So I'm going to share what I know well and then talk about how that might translate. And there's going to be a lot of math here. The goal is not to, make it so that everything is completely, you're not, you won't be completely proficient in everything if this is your first time seeing this. But the goal is that maybe it highlights some connections to things that are important and can give people some starting points for further exploration. So when we talk about these dynamical processes, there are a couple of different things. A dynamical process just means something changes. And a stochastic dynamical process is one where something changes in a way that is not completely predictable, where there is some element of randomness. I'm going to start with some examples of dynamical processes that are familiar, maybe. So the notation we're going to use is some people really like to use subscripts for these things, and I do not. So where other people might write x sub 0, x sub 1, x sub 2, ... I am always going to write it in function notation, which means the same thing. This means x is something I'm measuring at a particular time. These are equivalent ways, they're just different notations. And I prefer this one. But I want to say that so that if you look at a different resource and they use this subscript notation, it's equivalent. So I'm going to start with discrete time because I think from a perceptual level, we've experienced things typically as continuous time, continuous space. But when we're modeling it, often we start with thinking of it as discrete time. And then we start to think about the snapshots that we're taking as being closer and closer in a sort of an approximation of continuous time. So we're going to have a discrete time, and this is going to be a difference equation, which is a special type of discrete time dynamical system. And I'm going to start, there are two things you need for one of these. You need initial conditions, and you need an update rule. And this is true, you need these two things, no matter what you are working with, whether it's like an L system or a cellular automaton or a differential equation, you always will want to have some type of initial or boundary conditions and an update rule. The initial conditions tell us where to start, and the update rule tells us from our current state, how do we get to the next? So the example I want to start with is the dynamical or the difference equation specified by x sub 0 equals 3. That's my initial condition. I'm starting with 3 of whatever I have at time 0. And then my update rule will be x of t plus 1, which this is my next term, will be given by 2 times x of t, which is the previous term. Or I shouldn't say previous, I want to say now, the now term. So I start with 3, and every time step I double whatever I currently have. What this does is I can use this to generate a sequence of numbers according to this rule. So I would start with x of 0 is equal to 3. Now, whenever time ticks, my next step, x of 1, will be 2 times 3, which is 6. My x of 2 will be 2 times whatever my now term is, so 2 times x of 1, which is 12. And then my x value at time 3 will be taking the value at time 2 and multiplying it by 2. And I'll get 24. So this process generates a sequence of data that looks like this. And I'm sure you may have seen something like this before, but I'm wanting to work from the very beginning and build up because I just think that things go more smoothly that way. Are there any questions or thoughts about what we've said so far in terms of a discrete time dynamical system, and in particular, having this type of discrete time dynamical system? Well, I hope you're following this okay. And if you're not, please feel free to ask questions, or if you're following it and you think there are interesting ideas that emerge, please feel free to bring those up as well. So I could look at a similar type of rule, but instead of always doing exactly the same thing, I could have it where there's some type of choice that's made according to a probability distribution. So let's look at the scenario of what's called sometimes the random walk, or sometimes called the drunkard's walk in older literature, where we have a person who's standing at 0. Initially, and then every time step they flip a coin, and if the coin is heads, they move to the right, and if the coin is tails, they move to the left. And so we can track the trajectory of this person. So I'm going to have the same information. I'm going to have an initial condition, which is I'll start at x equals 0 at time 0. And then I'm going to have my update rule, which tells me how it should change when the next time step happens. So we're going to go left with probability 1/2. And we'll go right with probability. So this is now an example of a stochastic discrete time dynamical system, because we have this additional element of randomness that we're not always going to do the same thing. And now we cannot generate a single trajectory like we did before. Rather, instead of instead of a single trajectory, as time evolves, what we'll have is a probability distribution of where this walker might be. So I'm going to go through this a little thoroughly. When I start with x of 0 equals 0, because my friend here is starting on the number 0 here, no problem. But now, when I go to x of 1, I don't know whether they flipped left or right. So there are two possibilities in terms of what it could be. This is actually a probability distribution, or they could be at positive 1, and the probability that they're at positive 1 is 1/2. Or they could be at negative 1, and the probability that they're at negative 1 is 1/2. And sometimes it's helpful to draw a tree here. To show, okay, this, I'll put the probabilities on the edges. Yes. I see a hand raised, so I'm gonna stop for a second.
Sorry, I just wanted to know if your screen went. Oh, okay, sorry. I had
Yeah.
trouble seeing your screen.
No,
I was just trying to move it so I could see it. So sorry to interrupt.
no problem. I totally lost track of my own screen for a second. So I'm gonna put probabilities of 0.5 on each of these. And then when I go to x of 2, it becomes conditional probabilities, because now there's a 0.5% chance that I move up 1, and I'm now at positive 2. But there's also a 0.5 chance if I was at 1 that I move backwards to 0. And similarly, if I was at negative 1, there's a 0.5 probability that I went forward 1 to end up at 0, and a 0.5 probability that I went backwards 1 to end up at negative 2. So now for x of 2, again, it's a probability distribution or a random variable, where there's a 0.25 probability or 25% chance that I'm at positive 2. There's a 0.5 probability that I'm at 0, and there is a 0.25 probability that I'm at negative 2. And so what I'm generating here is a sequence of random variables where the next random variable depends on the previous one. But that's the fundamental difference in a stochastic difference equation, is that the differences are random, and so I can't speak to a single sequence of numbers. Rather, I'm speaking to a sequence of probability assignments. So I'm going to stop here for questions, because I kind of speed ran a whole undergraduate lecture there. But does that make sense? And are y'all okay with all this, or have questions about this?
I'm tracking and good. Thank you.
Cool. So where it becomes a bit more challenging for me is to now pass to continuous measurements rather than discrete measurements. I can do okay when the difference is allowed to be continuous. So here our our update rule was based on a discrete random variable that was only supported on plus or minus 1. So if I were writing this as a more formal equation, like how I wrote for the first one, I could do that. I could say x of 0 equals 0, and then my update rule, x of t plus 1, is equal to x of t plus b of t, where b of t equals positive 1 with probability 1/2, and b of t equals negative 1 with probability 1/2. And this would be a way where I'm taking this b of t random variable, which is just a coin flip, and now I'm writing this in my difference equation notation. And I'm putting this b of t variable for the coin flip. Other notation that we would commonly see is, so alternate notation here, would be to express this in terms of the difference. So instead of expressing it this way, I could also express it in terms of what is the difference between the next term and the previous term. And here I'm just subtracting this x of t term over. Or when we do this, often people will write delta. So another way to write this is the change at time t is equal to this coin flip random variable. And so this makes it look more like this emphasizes the fact that there's a difference here, because I'm expressing this in terms of a change operator. So if the symbols, for some people, symbols are like no problem. For some people, they're a little icky, but that's all. These all mean the same thing. What we could see instead is, instead of the change being expressed as a coin flip, the change could be drawn from something like a random. So what we had before was something where the difference possibilities, we might call it, was a discrete random variable. Instead of difference possibilities just being -1 or 1, we could see something where the walker takes a step, again, still equally spaced, but takes a step where the length of that step is drawn from something like a normal distribution with, let's say, mean equals 0 and standard deviation equals 1. And when we do that, it's still going to be possible to do this type of trajectory generation, but they won't look like these discrete tables. We will need to get into using information about sums of normal distributions, and we will know that, at time step 2, our possible positions are given by the sum of the two identical independent normal distributions from the previous 2 time steps. So it becomes a little bit less concrete in terms of just writing these out. But it's doable. And this would be something where we're looking at discrete time changes but the possible changes are coming from a continuous random variable. And then that actually creates our sequence of random variables. And then this is still just a stochastic difference equation, where it becomes a discrete, or where it becomes a stochastic differential equation is when we shorten the time steps. So that instead of there being, so that we're not thinking about there being any separation, but rather constantly the walker is constantly making a decision about whether or not to make a very small step. And over time, those instantaneous decisions add up. I don't have as good of an intuition for this, but the sort of go-to example for gaining intuition about stochastic differential equations would be to look at something like Brownian motion, where you have a particle that's constantly making, infinitesimal, theoretically, practically speaking, microscopic random movements, and over time that leads to the fluctuation in the market or the activity of the gas, but the actual prediction of any single market history or any single gas you can only say probabilistically. And the key challenge actually is going from understanding it as a single time step, to instantaneously each of these changes is happening according to some random distribution. So that's my best attempt at giving some lead up to it for people who haven't seen it before. I see you say double pendulum is my go-to. Would you like to expand on that?
Sorry, I'm trying to unmute myself, not be on video. No, I mean, in terms of like Brownian motion, like I think about like a double pendulum also, which is like you can predict the behavior with some probabilistic distribution, but it's like there's also an element of randomness. Um, it's not fully predictable the way that a single pendulum is. So there's some chaotic movement happening there, like similar to Brownian motion.
Is it stochastic or just chaotic?
Not sure.
Because I'm saying this as a general comment.
It's deterministic, so maybe it's
Okay.
not stochastic. So
Can I cross it out?
yes, cross it out.
Yeah, because that's actually something I struggled with a lot when I first looked at this, was the difference between chaos and randomness. And something can be unpredictable long term because the complexity of the rules aggregate and stack up, but it's actually not random at all. You'll always get the same answer 100 time steps from now with probability 1. Cool, we have an example and a non-example, and both are always really helpful. But again, I wouldn't, I called my friend who worked in finance, and he gave me some pointers on how to build intuition on stochastic differential equations. And we can continue exploring it, but basically I've told you everything I know about it at this moment.
So can you like just help me a little bit with the notation in the book? Like so I know like in equation A46, there's that random term omega that's like the normal distribution, maybe like it helps to augment the difference equation or the stochastic differential equation.
Mhm.
But so that omega, like so that's why I also think of the double pendulum. So I'm thinking in the wrong place. Like, so that omega to me looks um like an interval, but it's not. Like, so, but like that's why like my intuition is wrong here, you know?
Let me see. I'm pulling up the textbook now, A46.
Yeah, in the appendix.
Yeah, so
It says it's a random term with a mean of 0, so similar to your Brownian motion
mhm.
example. Um, but like so for me, that's why I go to the double pendulum, because I'm locked into that omega being like the interval from physics, but it's not.
Yeah, it's yeah, what this is doing is saying like the change is the change at every, instantaneous time step is drawn from um this normal distribution. So instead of flipping a coin, we're just sampling from like how much the particle could move left or right. And the explanation they give, I was kind of trying to follow this, although I probably could have used different notation. But they're saying if you look at a discrete difference equation with a discrete time difference equation, where at every time step you pull from a normal distribution, and then uh, you start to look at the time steps getting closer and closer and closer, so it becomes instantaneous or continuous time. That's like the actual probably rigorous way this is defined, and that's also helpful information. It says in a rather understated way, the interpretation of equation A46 is sometimes tricky. But this is saying that when you change, you're going to change. And whenever you change, how much you change by is coming from this normal distribution with a mean of 0. And I'm guessing this is a standard deviation of something.
Yeah, I struggled with that upside down L term also. Like what does that mean? I don't know.
It's a
And
it's a gamma, but I don't know what it represents here unless it's been defined somewhere.
it was not defined,
Oh, well,
which is like something that made me crazy a little bit.
that's
Um,
encouraging.
and then the tau is the time step, right? Like in A47. So like they flip back and forth between using tau as time and t as time. So
Mm.
it's just like a random bug in the system, I think.
Yeah, I'm a little bit obsessive. I'm probably gonna go and search for gamma later with copy pastes from this and see. There's
If you
surely,
can,
yeah.
right. So me too. And yeah, but now that like it's great that I have a much better understanding of the well, hopefully. If you can find gamma, let me know. But already like I know that I'm locked into like I'm locked into a deterministic system in my thought process, and it's not that way. So that was super helpful. Thank
Cool.
you.
I'm glad it was helpful, and I'm happy for us to continue exploring it. All
Yeah,
right.
like when I did differential equations, it was always or when I was studying this, the last time I studied this, it was always in a deterministic system because we're trying to predict the outcome. So
Yeah, and my background is in the discrete difference equations coming um, from either chaotic dynamical systems, something like the logistic equation, or I've done a lot with computer science algorithm analysis. But all of that is also I'm echoing that I'm more comfortable with deterministic, and I'm also more comfortable with discrete time in terms of my intuition. Um, Cheryl, I see you have a hand up, I believe. Is that from earlier, or do you want to come in again?
My apologies. No, it is from earlier.
No worries. I'm going to lower your hand if that's okay, and then
Please,
please feel free to raise it again.
no worries.
Yeah, cool. Um, so the other thing that this is like a personal request, I wanted to do this because it helped me with getting the definitions more stable, and also because I am a mathematician, if I can prove something, I want to. And what I wanted to prove, although proofs exist already in the textbook group documentation, was the equivalence of the different definitions of variational free energy. And so this will definitely get us into the weeds. It's, going to be technical and symbolic. But I feel it's worth doing. So on page 28 in chapter 2, equation 2.5 has a couple of different things that it defines, and it just says these things are equivalent. And whenever I see these things are equivalent, I want to know why, or at least I want verification that they are. So what we're looking at here is what's called variational free energy. This is a function that takes two arguments. The first is Q, which is a probability distribution of some kind. And the second is Y, which is some data that we have. What's important here is that there's just one Y. Like Y is, you can think of it as an observation, I believe is okay. And this is a single piece of data. I mention that because if that isn't, if we don't recognize that Y is a single thing that we're plugging in here, then some of the calculations, you're like, why am I allowed to do that? And I'll try to point out where that fact is important. So for what's going to happen, what we want to show is that a couple of these things are equivalent. So one of them is that we could define this as negative, the expectation according to Q of X apologies, I have somehow lost my pen. Okay. So let me switch back to this screen for a second. So this is what we want to prove, is that these three different things that are all presented as the definition or as representations of this thing are all actually the same. So I'm going to call the first one version 1, second one version 2, and the third one version 3. And the goal would be to take each of the different versions and show how we could manipulate them so they actually look like the other one. So I'm going to start with version 2 and show that you can manipulate it to become like version 1. And then I'm going to start with version 3 and show that you can manipulate it to become version 1. And then that will show that each of these three things are actually the same. So starting with this definition of, starting with version 2, if I start with the Kullback-Leibler divergence, this complexity term, and I say, okay, I'm starting with d sub KL, Q of X, double line P of X, minus I'm going to switch back to my whiteboard And hopefully the annotation will not abandon me. Cool. So I'm going to start with the version 2 that we just wrote, this d sub kl q of x double line p of x. And then I'm going to take minus the expectation over this q distribution of the natural log of p of y given x. And now I'm going to take, I'm just going to plug in what the definition of these things is from the actual place where they were defined. And so the definition of Kullback-Leibler divergence, which I had to look up because this would be the sum over whatever the possible x's are of q of x times the natural log of q of x divided by p of x. And then, so that's this part, the first term, the Kullback-Leibler divergence. And then I'm going to subtract off the expectation, which is the sum of q of x times the natural log of p of y given x. And now I am going to use properties of logarithms, and I'm going to replace this part with something that it is equivalent to. So this will become the sum over x and x of q of x times natural log of q of x minus natural log of p of x. And then in the interest of space, I'm also going to replace something here. I'm going to replace the fact, I'm going to replace this probability of y given x with an equivalent way of rewriting it, which is q of x times natural log of, and an equivalent way of writing the probability of y given x is the probability of y and x divided by the probability of x. And now I'm going to use properties of logarithm again on this part. And again, the log of a ratio is equal to the difference of the logs. So that will become the natural log of p of yx minus the natural log of p of x. So let's write all of this out. I'm going to write them on two separate lines because it makes things line up a little bit nicer. So this becomes q of x. This first term just stays the same. And then this new term where I'm introducing the log property becomes natural log of p, the joint distribution here, minus natural log of p of x. Can you see what's going to happen? There are a couple of terms that will cancel once we write everything out. So what I'm going to do now is distribute this through. So this first one becomes I'm going to take this q of x and just distribute it through to the logs, and I'm going to take this q of x and distribute it through to the logs. So this becomes the sum over x and x of q of x, natural log of q of x, and then I can split the summation here. So this becomes the sum of x and x, q of x, natural log p of x. And then if I distribute this minus and this q of x through, this becomes minus the sum over x and x, q of x, natural log probability of y and x. And then this minus minus cancels and I get plus sum x and x, q of x, natural log p of x. And this term is the same as this term, just with signs flipped, so these cancel. So what I'm left with here is the sum over x and x of q of x, natural log q of x, minus the sum over x and x of q of x times the natural log of p, probability of y and x. It turns out that this is the definition of entropy up to a minus with multiplied by -1. So this would be the minus of the entropy of q of x. And that this is the expectation over the q of x distribution of the natural log of the probability of y and x. So what we did was start with one way of writing this, unpack what all of that actually was defined to be, use some algebra, properties of summations and logs, and end up with version 1 of the same formula. So this shows that version 1 and version 2, as we called it, actually do represent the same thing, because they can be, one can be manipulated to be exactly the same as the other. So version 1 is equal to version 2. I'm not necessarily expecting, also I made a mistake here. This E is not symbol for entropy, it's a symbol for expectation. So this should be in H. So here we have. So if you look at equation 2.5, I believe it is, says these two things are equal, and now we know for sure that they are. And if you want, it might be a fun exercise for you to play with it and see if you can get the same thing or if you agree with me. But the big value that this added for me was getting more comfortable with the definitions. Any thoughts, questions, or comments on that? Zoom here to get the entire thing on the board. So the other thing we need to do is start with version 3 and end up with version 1. So we're going to start with, thank you for coming. I hope you can come back next week. So we're going to start with version 3. I'm going to write the starting point, which is my version 3 here. Again, starting with the Kullback-Leibler divergence. And here I'm minus the natural log of the probability of y. So if I write out what that means, I'm just going to write out the formula here. I'm sorry, this is the probability of x given y in this version. So this is probability of ln of q of x divided by probability of x given y. And then this other part doesn't change. So minus the natural log of p of y. And this becomes the summation of, so I'm going to do the same thing I did before where I take this natural log and split it up. And I'm also, that's probably enough for one step. Okay. And then still minus this natural log of p of y term. Now I'm going to do the same thing again where I look at what is the definition of the probability of x given y. And I'm going to rewrite the probability of x given y as the probability of x and y divided by the probability of y. And still minus the probability of natural log of probability of y. Now we can do the same trick again, where we take the log of the ratios and turn it into the difference of the logs. So what this becomes is sum q of x of natural log q of x minus natural log probability of x and y. And then because I'm minusing a minus, this becomes plus natural log of p of y. Minus natural log of p of y. Now, if I were doing this for a regular class, I would have people who wanted to just go ahead and cancel these two natural log of p of y terms, and that's not going to work. So what we need to do is take this q of x and distribute it through everything. And while we're doing that, we can go ahead and split the sums up. So this is going to be the sum over x and x of q of x natural log q of x minus the sum over x and x of q of x natural log of probability of x and y. And this equation continues. We have plus the sum over q of x natural log probability of y. And all of this is minus this natural log p of y term. Now, if we were looking ahead to think about what we wanted to end up with, we really just want the first two terms. And this sum over x and x of q of x natural log of p of y is annoying. So what we can do is factor this in front. And now I'm going to erase and rewrite for interest of space. So what this becomes is natural log of p of y times the sum over x and x of q of x. Because this natural log of p of y was just a constant, so we can pull it in front. And then the key insight here is that this sum over x and x of q of x is equal to 1, since q of x is a probability distribution. So I can take this summation and just turn it into multiplied by 1. which means that this term and this term actually do cancel. So when I take this natural log of p of y minus natural log of p of y, I just delete both of those because they cancel. And here again, I'm left with the negative entropy of q of x minus the expected value over the q of x distribution of the natural log of p of xy, which is equal to version 1 of the variational free energy formula. So mathematically, all three ways of writing this are actually the same. And algebraically, and you can rewrite them so that they work out to be starting with one, you can get to the other. And that's the cool thing that I enjoyed doing. But also doing that helped me internalize and make more definite some of the definitions of the formulas, and to get an understanding of things like, why is it negative entropy instead of positive? Why is it important that y only be a single observation? There are other versions of the proofs that are well explained that are available in the coda. So I'd encourage you to look at those as well. But mainly it's just about, I think the proof is worth doing for multiple reasons. I do need to go soon, or do y'all have any thoughts or questions before we dismiss? And if you have any longer thoughts or questions, let's discuss them in Discord and bring them back to this meeting next week. Cool. Well, thanks for coming out, everyone, and I'll see y'all in a week.